Okay, so recording has started and we will begin our session. So, good evening, everyone. So, this is our week 7 live interaction session for the Aspen Plus Simulation Software course. This is a basic course for the beginner. And if you have been attending my interaction sessions, so I'm Bhavesh Moorjani. Brief about me that uh, I have done my bachelorates from MS University, Vadodara, and then after that I was working at Gujarat State Fertilizer for some time, and then I'm currently doing PhD at IIT Bombay, and I'm a course TA for this subject where I do this live interaction session to get you guys more familiar with the Aspen Plus software by doing more practical problems on the software itself. So my session is on Tuesday every week from 6 to 8 p.m. Similarly, there is another TA, Rajdeep Mukherjee. His session is on Saturday 6 to 8 p.m. Okay. So if you have been following and attending lectures regularly, so what you will see in the course outline by Professor Saha, what we have done till now, till part of the week 6, was to do a process plant simulation of some model of the Aspen Plus to get familiar with that model. So we have dealt with all of these models which are available in the Aspen Plus, be it be separator, mixer, distillation columns, adsorption columns. So we have seen this mixer splitters, separators, heat exchangers, basic heat exchangers, to going into the detailed design of the heat exchanger. Similarly for the columns also, like how to do simple FUG method calculation to a detailed column internal calculation, right? Same way we saw different types of reactors that can be used in the Aspen Plus simulation, pressure changes, right? So overall the idea till week 6 was to get familiar with this all the various models that are available, how to do various property analysis, how to utilize Aspen Plus for this small aspect. Now from week 7 onwards, sir has started various case studies where small process plant operation will be simulated in the Aspen Plus to find various properties, separation, desired separation amount, or anything. Okay, I mean related to the actual process plant problem rather than just working with a small unit. So the way I have designed to this week's lecture is that first we will deal with the basic problems which are related to the distillation column and reaction engineering, and then we will move forward with the case study which is a series of distillation column, and from the next class onwards we will dwell into the more detailed and slightly complicated problems which will involve multiple unit operation as well as processes in a simulation. Okay, so let us begin today's class with the problem solving approach. So just a brief announcement, like if internet connection issue happens or you get disconnected from this meeting, just join this meeting again. Just wait for 10 to 15 minutes. If any issue occurs from my side, I will join it again. Okay, you don't have to leave, you can wait for 10 to 15 minutes, I will join again. Yeah, so with that said, let's begin with the today's class. So we have first problem which is on the distillation column part. Just a minute. Yeah, recording is also on. Okay. So first problem that has been given to us is related to the distillation column unit. So we will recall some of the previous simulation that we have done so far. Okay, so the problem statement says that a feed consisting 45 mole percent of propane and 55 mole percent of isobutane is to be separated by distillation. Feed flow rate is given as a 25 kilomole per hour, and temperature pressure conditions are 325 Kelvin and 20 atmosphere pressure. Okay, so first we have to perform a shortcut distillation design using Wien, Underwood and Gilliland method to get 90% propane separation in the distillate. Heavy key recovery is given as 0.1, this should be 0.1%. let's say 0.1%. And the number of stages of the column should be 15, that is given with a condenser and reboiler pressure also provided. The method that we have to use for property estimation is also provided, and then we have to answer the following question. So first let's do the normal DSTWU simulation, which is a basic distillation column design using Underwood and Gilliland method. Okay. So the component here we have propane as well as isobutane. So first let's just add this component. Okay, for isobutane, let me just search. Why I'm having this issue. Let's say C4H10. Let me search by this. Okay, let it load. I don't know, I find this issue with searching compound. I don't know whether you guys are facing same issue or not. Let me do ice C4H10. Just give me a minute. It's taking too time. Let me reopen it. If not, then I already have this example done. We can directly look into that also. See whatever opens up first. Mm. Uh, is any one of you can share your Aspen Plus screen? Is it possible? If you have access to Aspen Plus right now, and can you share your screen so we can do problem there? Jamie or Rohan, can you share your screen if you have an access to Aspen Plus? Is it possible? Yes, no? Oh, I guess you don't have an access right now. Okay, then let's wait. It's not loading. Why this is starting? Record. Guys, is it possible if you can share your screen, because it's taking too long to load in my PC right now. Don't worry, I will guide you if you will share your screen. No. Okay. Just give me a minute. By that time, let's look into the problem statement. So after doing the normal distillation DSTW simulation, here we have been asked to find the reflux ratio, feed stage, what will be the reflux ratio for stage 17. Okay, and then after that we have to perform a rigorous calculation for the same feed stream using red flag column for same number of stages molar reflux ratio, but the distillate to feed ratio has been changed. Condenser type is still total, and operating pressure is slightly changed. No, or is it same? 16.8 atmosphere. Feed location is given and the pressure drop across the column is 0. Then we have to perform a sensitivity analysis by varying the reflux ratio from 2 to 15 with an increment of 0.5 to tabulate the propane mole fraction in a distillate. So let's see. Yeah, it's loaded. So here first what I have done, so here we have added the component propane and isobutane. Then the method. So method that has been given to us is this Chiave. So this is a defined method in the problem statement, so we don't have to worry about it. If nothing is given, then we can use the method assistant tool to find out what method to select here. Okay. After that, run the property analysis and then go to the simulation tab. Guys, just a minute, okay? I think recording, there is some issue in recording. So it's working correctly now. So I was saying that we have added the component propane and isobutane. Select the method, run the property analysis, and then go to the simulation tab. Here, as you can see, I have already done both the calculations. We can just quickly look into that, and depending upon time, if we have a time, we can revisit this problem again. So we have feed, which is coming at, if you will see the feed input, feed is coming at 325 Kelvin and 20 atmospheric pressure with a flow rate of 25 kilomole per hour, and the mole fractions are given. So that is the defined problem statement. Then feed goes to the our DSTWU column. Okay, so that is a B1 column, and the input of B1 column. So we have been asked that we have total 15 theoretical stages. Total number of stages of the column are 15, with a condenser and reboiler pressure given, as well as the light key and heavy key recovery is also provided. So we have added the light key and heavy key component recovery. So light key is 90% and heavy key, sorry, then it might not be 0.1, it's a point ratio, 0.1. Add both of this data and run the analysis. So what you will get here, if you will see stream result for the block B1, which is DSTWU unit, what have been asked to us. First is what is the actual reflux ratio of column with a 15 number of theoretical stages. So for that, go to the result of B1, and you can see actual reflux ratio is 2.15493. So is that the answer? So answer is within the range between 2.15 to 2.21. Then second question is the feed stage of the column rounded to the nearest integer. So we can find the feed stage is around 8.13, so that is 8. Is it the answer? Yes. Then the reflux ratio is at stage 17, obtained from the reflux ratio profile. Now to get a reflux ratio profile, there are two ways. Like here one option is given as reflux ratio profile in the input block here, in the calculation option. I had already selected this generate table of reflux ratio versus number of theoretical stage. Let's say if we don't select this, then in the result part we won't be getting any profile. But here we have selected the general, we have put tick marks on the generate a table for a reflux ratio versus number of theoretical stage. Thus on the running the simulation, we will get this reflux ratio profile, where along with the change in the number of theoretical stage, we will find how reflux ratio changes. Here one more thing, in this calculation you can provide initial number of stage to final number of stage, how much area that you want to explore, how many distillation stages you want to explore, and corresponding reflux ratio will be given. Okay, so right now we haven't provided anything, so it has taken default value of 11. Okay, so it has given the result for 11 number of points from 10 to 20. And if you will see, what has been asked to us is the reflux ratio at stage 17 obtained from reflux ratio profile. So for if 17 number of theoretical stages, reflux ratio is 2.00063. which is in between 1.98 and 2.04. So that was the basic DSTWU calculation. Now we have been asked to perform a rigorous calculation using a red flag column. So if you will go into the main flow sheet, here the heat stream is duplicated and it's going to this red flag column, B2 column, the input of B2 column. So we have been asked to that number of stages are same as the previous model, 15 number of stages, and reflux ratio is also same. So if you will see this theoretical number of stages are 15. Total condenser we have used previously also. Reflux ratio 2.15, which is selected from DSTWU unit. And then distillate to feed ratio has been provided in our question, so that we have to select it as 0.42. Feed is entering at stage number 5, that has been added. Pressure value of condenser is given as 16.8 bar, and what has been said that there is no pressure drop, so assume the zero pressure drop in the column, so that's why the stage pressure drop has been considered as 0. Thus all the inputs are complete, and once we run the simulation we get the corresponding result for B2 block also. So for that, what has been asked to us, we have been asked, first is the mole fraction of propane in the distillation for the molar reflux ratio of 14. Okay, so now here the reflux ratio that we have selected, if you will go into the B2 column result from results, yeah. So current reflux ratio is 2.15, but what has been asked to us is the mole fraction of propane in distillate for a molar reflux ratio of 14 is blank. Now here, unlike the DSTWU unit, where in the input section we had this calculation option where we calculate the reflux ratio with number of theoretical stages, in the red flag column, in the input option we don't have such option. Okay, so if you will see the setup part or specification part, we don't have any option here. So in that case we can perform a sensitivity analysis that we have done in the last week. So for that, here you can see in the model analysis tool we have added the sensitivity S1 property, which is nothing but the change in the mole fraction of propane with the number of with the variation in the reflux ratio. So we have selected the input variable, which is block variable B2. This mole RR is nothing but a molar reflux ratio. Start to end point is given, like starting from 2 we have to go through till the 15 with an increment of 0.5. This is our manipulated variable, and calculated variable will be propane mole fraction. So that is a stream property which distillate coming out from the red flag. So here you can see this D red is nothing but the top product coming out from the red flag column. So that has been here. So that has been specified, mole fraction of propane in the mixed stream D red, that we have to calculate. This property will be calculated, and in the result you can see here we have the profile. If we can plot it also, our x-axis will be reflux ratio, y-axis will be propane mole fraction, and when we get this sort of a graph. Now what has been asked to us at stage number 14, like with the reflux ratio of 14, if the molar reflux ratio is 14, then what is the mole fraction of propane? For that you can use this graph also here, show tracker, and check it out. For 14 we have value of 0.976, somewhere around 0.9766. We can also see in this result part also where we have exact value. So for reflux ratio of 14, propane mole fraction is 0.976648. So here the answer is 0.973, between 0.973 and 0.979. So our answer is in between. So that is correct. Second question is asked, is the viscosity of distillate. So let's go to the stream result for the B2 block. In the B2 block, what we see here, This is the stream result. At the end, we don't see any property for the viscosity. We have temperature, pressure value, molar enthalpies, mole flow, mass flow, mole fractions. We have volumetric flow rate also, but we don't have this property added. We don't have the value of viscosity. So how to do that? For that, we will use this add property option, and we will search for the viscosity. So you can see the viscosity of mixture is there, viscosity of pure component is there. So let's say I just want to see the both pure component viscosity as well as mixture viscosity in a stream, that we can add. And once you add that, now you can see here we have viscosity also added. So we have viscosity of mixture in centipoise for feed, bottomlet and the top distillate part, and then for there we have individual component viscosity also. We have been asked viscosity of the distillate, which is 0.07485 centipoise, so which is 0.0785, like in between value, right? 72, we have 74 value. So this is the just basic example of red flag column that we have already done it. Now we will move forward with the example of one reaction, and after that we have another example. No, this is a case study. We have one more example of reactive distillation, and this PFR reaction into the PFR column. Okay, so this is the end of the first question. Let me open a new file and hopefully it works now. Yeah. No. So what is the second question? Second question says, in the acetic anhydride manufacturing, the cracking of acetone produces ketene and methane according to the following reaction, where acetone breaks into form a ketene and methane. The reaction is first order reaction with respect to acetone. Feed condition as given, the feed coming at 130 kilomole per hour, which enters into the plug flow reactor at a given temperature and pressure condition, and the kinetic data for corresponding reaction is given. Here what has been said, the unit of pre-exponential factor indicates the CI basis, which is molar concentration basis of the rate constant, that is fine. The use of Langmuir, Hinswold, Hoog and Watson LHHW kinetic model has been done. So what is this? Do any of you know this model, this kinetic model? So this is nothing but for this model is particularly for a reactive, not for a heterogeneous catalytic system, like heterogeneous reaction system. This model is used. So if you will see, should be here. This is a research paper which talks about the use of this LHHW model for ethyl esterification of fatty acid. That is not our concern. I wanted to show you this. So for a surface reaction, if you will recall your CRE2 phenomena for the kinetics for heterogeneous reaction, we have multiple steps occurring during the reaction. First, we have a diffusion of your reactant to the heterogeneous surface. Then you have adsorption kinetics. Then you have reaction happening on the surface. Then desorption, and then again diffusion of product from surface to the bulk phase. Right. So this LHHW kinetic model is nothing but a kinetic model for surface reaction, which is a kind of a slightly modified version what you will find here. So this Wikipedia page talks about the only Langmuir-Hinshelwood mechanism, okay, which considers this. So this is your reactant A, which comes to the surface, is getting absorbed. Similarly, reactant B comes to the surface, gets absorbed. Then reaction happens. Then from here, desorption part will happen. So there are multiple ways to represent the kinetics of such surface reaction. And in this LHHW model, rate is represented by the combination of kinetic factor, driving force, and adsorption expression. Where kinetic factor is kind of similar to your Arrhenius equations, where K is equal to K0 exponent minus E by RT. If you have a T0 as a reference, then you can write expression in this way. The driving force, this is a driving force for the absorption that has been given, and then adsorption expression is followed by this expression. Okay, you can also use the K. The exponential factor can be also dependent on the temperature of your system. Okay, so this two data is given. So instead of using normal power law model, we have to use LHHW kinetics model. You can study about this model more on the web itself. Right now I am just giving a brief overview. In that model, we have been asked to set 0 for all coefficient under term 1 and for all coefficient except A under term 2. We will see when we will set up the reaction. Take a very large negative value of coefficient A. PFR dimensions are given, 3 meter length and 0.6 meter diameter, and we have to use this Bayes method for property calculation. So let's go here. Let's add our component. We have acetone, then we have ketene, and methane. Last, we have methane, okay. Go next. The method that has been asked to us to select is this method, which is run the property analysis. So results are available and there are no warnings. So let's go to the simulation panel. We have to simulate plug flow reactor. Connect the reactant and product stream. Let's rename it. So this S1 we have reactant and then S2 will be our product. And this is our PFR reactor. Go next. First add the feed condition. So feed is coming at 130 kilomole per hour flow rate with a temperature 725 degree centigrade and 1.5 atmospheric pressure, and we have pure acetone. So 725 degree centigrade and 1.5 atmosphere, so that we will change. Flow rate is given as 130 kilomole per hour, which is pure acetone. So let me write 130. Rest of the things are 0. So ketene and methane will be produced during the reaction part, in the PFR part. Go next. Let's add the input for plug flow reactor. Now for the plug flow reactor, here we have been asked the plug flow is a adiabatic PFR with 3 meter length and 0.6 meter diameter. Okay, so select the reactor type. We have a adiabatic reactor. Its configuration, so length is given as 3 meter, diameter is given as 0.6 meter. Now the phase, here one thing to take care of is what will be the phase of the reaction. So here we have different options, whether the process stream are in the vapor phase, liquid phase, vapor liquid, and this selection will affect our calculations also. So you have to be very careful when you are selecting this. So in our streams, if you will see our reactant or our feed, which is a relatively very high temperature of 725 degree centigrade and low pressure of 1.5 atmosphere. So we are sure that feed is at vapor condition only. Thus, in the configuration part, we have selected valid phase as a vapor only. If you have a liquid phase or a mixture of both, then we have to select vapor liquid. Now add the reaction part. In the reaction, we have to select the type of the reaction. So previously what we had done either this general or power law model we had selected for the reaction part. But here we have been specified that we have to use LHHW model. So select that. Go to the specification part of the reactions, R1, and we want to provide the input for R1. So let's add the reaction. Reaction is this acetone decomposes and produces ketene and methane with a coefficient as 1, 1 and 1. For the kinetic part, since this is a different LHHW kinetics, the rate expression is represented by the combination of kinetic factor, driving force expression and absorption expression. Okay, now we have been given the kinetic data. That rate is 1.1 second inverse. We will specify that. N value is given as 0. Activation energy is given as 28.5 into 10 to the power 7 joule per kilomole. So we have 28.5 e to the power 7. Okay, so it has changed it and written it in its form, 2.85 into 10 to the power 8. And the T0 value is given as 980 Kelvin. Okay, so let's put that 980 Kelvin. You will see still it hasn't turned blue. so there is still input incomplete. For that, as this reaction kinetics just does not work on the kinetic data, it will need also either the driving force expression or the adsorption factor. So here we have been given this driving force expression. If you will see the problem statement, it says the unit of pre-exponential factor indicates the C1 basis, which is the molar basis, and that are selected, like molality is selected here, Ci basis. Okay, we don't have to change it. The term 1 for this kinetic expression, so it has been said that set 0 for all coefficient under term 1 and for all coefficient except A under term 2. So here you can see we have coefficient for driving force constant. So we have been asked to put 0 for all. So A, B, C, D all are 0. Now here the exponent for the reaction part, so it's a first order reaction in terms of the acetone. So we will put it as 1. Rest can be 0, so we don't have to specify it. And for term 2, we have been written that we have to set all coefficient 0 except A, and for A we have to take a very large negative value. Now why these specific conditions are given? Because this is the way how calculation of this reaction kinetic works. So it has nothing to do with any process aspect or the simulation aspect, but the way the method works. Okay, so let's provide some high value of -1 into 10 to the power 6. Okay, do next. All the inputs are complete. Let's run the simulation and see what results we are getting. By the time after this we have another example of reactive distillation. So if I recall, in our interaction session we haven't done any reactive distillation part, so that's why I have added this example. Obviously sir has taught it in his lectures, so we will do this reactive distillation example, and then after we will move forward with the this distillation column in series example. Okay. So results are available. Computation order of the flow issue. Warnings were issued, no errors. Warning in physical property. This is fine. So the simulation is complete, and we can check the stream result for the PFR stream. Here what we are getting, that it's a mole fraction and mass fraction. Oh, there has been no conversion happened, like we are getting acetone completely. Probably some mistake has happened here. Let me check. R1 is added. Reaction has been added, then what's the issue here? Okay, 1.1 and 0 joule per kilomole. Yeah, see here, the reacting phase has been selected as liquid, but in actuality we have vapor phase. If you will see the stream part, the temperature is 725 degrees centigrade, which is very high, so we have vapor phase. So here the mistake I made is that reacting phase was selected as liquid by default and I haven't changed it, which should be vapor. Okay, so now that we have made these changes, let's rerun it. First let me reset the simulation and run it. Let it load. For this third problem, for the reactive distillation part, do any of you want to do it on your PC, or should I do it in my PC only? If you have access to Aspen Plus and would like to share your screen. Question number 3 I am saying, which is for reactive distillation column. It's a simple part where along with the distillation we will also add the reaction. So anyone want to volunteer, either Rohan or Gaurav? I guess no. Okay. Anyway, then you might have to slightly wait. Okay, so results are available here. So go to the PFR block and the stream results. Now let's check the mole fractions. Yeah. So we observe the conversion of acetone being converted to ketene and methane. Okay. Now very few amount of acetone has been converted. If I look at the moles, we had 130 kilomole per hour flow rate of acetone, and in the product stream 112 kilomole per hour, around 112 kilomoles per hour acetone is present. So if I want to see how acetone conversion is happening with the length of the PFR, for that we can do a sensitivity analysis. First, here in the profile section, let's visualize what result we have. If I look along with the reactor length, what is the molar vapor fraction and check it. Not molar vapor fraction. We should get composition here. composition is not here, sorry. Let me go, let's do a sensitivity analysis and see with the change in the length of the PFR how conversion is happening, like how is there some issue on this? Oh, I lost my connection. Oh, yeah. Sorry for this, I think there was some internet issue. Okay, so my screen is visible, right? Yeah. So here I was saying that in the stream result we find very little conversion of acetone happening. So then we want to check if we increase the PFR length whether the conversion will increase or decrease. So for that we can perform a sensitivity analysis. So go to this model analysis tool, go to sensitivity part, add a new S1 property. Here we will add block variable, since we want to check how varying the length of PFR will affect the conversion. So let's search for the length of the reactor, select this as a parameter, start value let's give 1 and end value let's say 10, and number of points I want in between is 50. Okay, let's define our variable, which is mole fraction of acetone. Okay, that's a stream variable. We want to know mole fraction of product stream, and that to acetone value. Fill all the variables and run the simulation. Yeah, so results are available. So if you will go into the result, let's plot it out. How does this profile look? So we have x-axis as a PFR length and y-axis as mole fraction of acetone. So you can see with the increase in the length, mole fraction is decreasing. So then we can decide at what value, how much conversion we want. Then according to that we can decide what should be the length of the PFR. Now here this we have only varied the length. Similarly we can vary the diameter also and decide the optimum ratio of length to diameter for PFR for our desired conversion of acetone to ketene and methane. Okay. So that was the one part for the reaction in the PFR column. Now we will move forward with the reactive distillation example. For that, let me start a new simulation. Let it load. Okay, one more student has joined. Hello Nikhil. How to solve license error? I think license error was already solved, right? Previously. Are you guys facing an issue again with license? Better to write it out to NPTEL team, or maybe keep a loop, Professor Saha in a loop. So Since the license part they are dealing with, I am not aware about what are the issues. Okay, but if you guys are facing an issue with the license, then you can ask Professor Saha directly or the NPTEL team. They will resolve it. Okay. Do any of you want to do this example again? Reactive distillation column. Nikhil, do you have an access? I guess you don't have an access to Aspen Plus right now. Okay. Anyway, then if you don't want to share your screen, I will do it, but you just have to wait for a few minutes. So the question number 3 says that we have a reactive distillation column where decomposition of HI to hydrogen and I2 is considered. Okay, and the column has total 8 stages, including a partial condenser and a reboiler. An operating condition is given as 22 bar. Feed condition is given, temperature, pressure value, flow rate, feed stage, as well as reflux ratio, and a distillate to feed ratio has been provided along with the feed composition. Now for the reaction part, the HI decomposition reaction is taken from this reference research paper, where it's a reversible reaction. It's an equilibrium limited reaction taking place in the vapor phase. The chemical equilibrium constant is given, which is a function of partial pressure of a species. Okay, and the expression of HI decomposition, chemical equilibrium constant as a function of temperature is also provided. K equilibrium as a function of temperature is provided. Reaction is occurring between 2nd to 6th stage, and we have to use NRTL property method to simulate the reactive distillation column. So that's our problem statement. Now once this loads, we can move ahead with the question. Okay, so we have total 4 components. Water is also present in the feed, so we will add this all 4 components. So first we have HI, it should find it based on its chemical formula. Then we have hydrogen, iodine, and then last we have water. We have been asked to use an NRTL method, so let me select that and run the property analysis here. corresponding in physical property NRTL binary parameter for all component pairs are 0. Your result may be accurate, not be accurate. Okay, so there is some issue with the binary component parameter. That for that, go to the parameters and the binary interaction for the NRTL method. Okay, so there are no binary components present, so we can estimate them by a unifact method. Results are available. So this is done, property analysis is done. Let's go to the simulation part. Now we have to do reactive distillation. For that we know the red flag column itself is useful for a reactive distillation column design. Select the red flag column. Provide the feeds, input, output. So we have feed, this is the top product. So let me say red flag top and red flag bottom part. Okay. Now go to the next and provide the feed condition. So what has been said that feed temperature is 532.78 Kelvin. 532.78 Kelvin, and the pressure conditions are 22 bar. So 22 bar pressure. Flow condition is given as 150 lph liter per hour. Okay. So instead of total flow, molar flow, I will select the volumetric flow rate. Volumetric flow rate, that too liter per hour, and that value is 150, and we have been mole fractions are also provided. So let's put it as 150 and the mole fraction. So we have HI 10%, water 0.51%, sorry, not percentage, 0.1, HI, H2O 0.51 and I2 0.39, 0.1, 0.51 and I2 0.39, while hydrogen is 0 in the field. Okay. Do next, and then it will ask for the specification of the red flag column. So here what has been said to us that the column has a total of 8 stages including partial condenser and reboiler. So total stages are 8. We have to provide a partial condenser, so either partial vapor or liquid. So let's say consistency error. Okay, so here we have selected the partial vapor part. So if we are selecting condenser as a partial vapor, then the top stream coming out from the reactor should be vapor stream. So let me select this red top, reconnect it to the vapor part of the red flag column. Okay, now this error should not come. So if I select so partial vapor that we have selected, then what else has been asked? So reflux ratio is provided as 3.5 and distillate to feed ratio is also given. Let me copy this. Reflux ratio is 3.5. Distillate to feed ratio, that is given as 0.55575. Okay. Now the stream specification. So feed is entering at stage number 7 above the stage. So feed is entering from the top actually. Pressure conditions. So what has been given to us? That 8 stages. Column is like this. Feed is at 22 bar, but what about the column? We should use the NRTL method. Okay, so nothing is said about the column. So we will, okay, yeah, column is also operating at 22 bar pressure. So column is also operating at the same condition. So that write condenser pressure as 22 bar. And pressure drop across the column, I will write it as 0. These things are added. We don't have to provide this other optional parameters. But now we have added the right flag parameters. We also want to include the reaction part, right? So for that, if I will go into the reaction, we have to select reaction which is happening between stage number 2 to 6. So in the reaction part, we have been asked starting stage for the reaction is 2, ending stage is 6, and reaction ID we have to provide. So we haven't defined any reaction ID yet. So create a new reaction ID R1. Okay. Now we have to provide specific parameters for R1. So if you will go into the reaction section, R1 has been added. Go to R1, add a reaction. So we have a kinetic equilibrium part where HI is decomposing and forming H2 and I2. What are the coefficients? So 2, 1, 1. This is the equilibrium part. So we have added, just a minute. Cannot access this. Yeah. So we have added the coefficient for the reaction. Exponent we don't have to worry about because we are currently dealing with the equilibrium rather than the kinetic part. And in the equilibrium, we have to provide conditions. Okay. So here what is said that this HI decomposition is equilibrium limited reaction, which is taking place in the vapor phase. So our valid phase, reacting phase should be vapor only. Select consistency error, K base molar. Yeah. So this anyway we are going to change. What it is saying, for the reacting phase vapor, K equilibrium should not be dependent on the mole fraction like mole gamma, rather than it should be partial pressure. So if you will see, if I put my cursor on the partial pressure, it is written when selected the equilibrium constant is a function of partial pressure into partial pressure to the power stoichiometric coefficient, and that has been also provided in that equation, like in that problem statement also, that K equilibrium is a function of partial pressure of H2 I2 divided by HI, that to the power of stoichiometric coefficient. So this selection here is correct. We have been also given the K equilibrium built-in expression. So we know the value of A and B. So let me just copy paste this value. A is minus of this. See, this is the expression. So we have two coefficients A and B. C, D are not provided, so you can assume it to be a 0. B value is minus 27722. So negative of this. Go next. All the required inputs are complete. Let's run the reaction. Processing the input specification. While it's loading, what happened? There is no available tank in Aspen Plus. Can I ask question? Yes, Nikhil, go ahead. You can interrupt me in between also. What doubt you have here? Yeah, there is no option of tank in Aspen Plus because it's if I can share this screen. Hi, you can share your screen. Just wait a minute. Anyway, this is processing. So while it process, you can share your screen. What issue you have? Nikhil, can you share, speak it out what issue you have? I'm not getting it. What you are saying? What exactly you want to show me? Can you pause there? Yeah. Tank volume is given as 15 meter cube which fills in 1 hour. Inlet pressure, pipeline specifications are given. Find out pump power required, available NPSH pressure drop. 1 atmospheric pressure, 2 hours, pump power required. So this is kind of a batch problem rather than a continuous process plant problem. So you want to solve this problem using Aspen Plus, if I am understanding from your question. Is it right? So you want to solve this with Aspen Plus.
So how to solve in Aspen Plus cooking not available in tank?
Yeah, so we don't have a tank option, but you can, if it's a continuous process but your tank volume is specified as a 15 meter cube. So anyway, at one point it will run out of, you have to stop the pump, right? So rather than that, looking at it as a batch problem, you can design it in terms of the continuous operation. So where you specify
how to simulate, कैसे करेंगे सर simulate? How to simulate in this problem?
How to simulate? So you decide some flow rate. Let's say you want to pump it out at a flow rate of 5 meter cube per hour. Okay, so you have a one flow rate, and total flow is total volume of tank, So that means, let's say if 15 meter cube is your tank volume, and you are flowing, you are pumping it out at a rate of 5 meter cube per hour. So then you have to run pump for 3 hours only. Okay. So then you have converted your batch problem into continuous problem, which will run for 3 hours. That is fine. And the question that has asked, like the NPSH of pump and other part, so that are fairly dependent on the flow rate part, right? So once you know the flow rate, what are the specifications required in the pump part? That is, your inlet feed will come, its condition, temperature, pressure and the flow rate. What should be the discharge pressure of your pump? You provide that and it will do the calculation for NPSH and other stuff. You are getting it? Yes or no, Nikhil?
Yes, sir.
You got the idea what I am saying here?
Exactly, sir. मैंने off किया था SPs, but over.
Yeah, because you cannot design. I said, since it's not a batch problem, आप उसको batch के problem पे कम करने.
DWC में exactly possible है, पर Aspen test में भी possible हो सकता.
So Aspen test में it's a batch operation नहीं होता है, it's like continuous operation. So you आपको उसको continuous problem के terms में convert करके देखना पड़ेगा. Then you will be able to do it.
So convert कैसे करेंगे और convert?
So that's what I'm saying कि you considered some flow rate of a pump and then proceed ahead with that rather than looking at it's a batch problem.
मैं consider flow rate को consider क्या करेंगे? मैंने कितना भी ले सकते हैं, मतलब negative pressure भी हो सकता है ना, अगर हम pressure flow rate को decide करें.
हाँ, so you decide some practical flow rate, right, which is possible. I mean problem specification में और चीज़ें भी तो दी हुई होंगी ना.
सर फ्लो रेट को चेंज करके फिर नेगेटिव प्रेशर में आ गया था, एरर आ गया.
नेगेटिव प्रेशर आ रहा था,
चेंज करा बार बार फ्लो रेट.
देन यू कैन ट्राई मल्टीपल थिंग्स एंड व्हाट जैसा मुझे दिखा आपके क्वेश्चन में से, सो इट्स जस्ट नॉट रिलेटेड टू मोर ऑफ अ कैलकुलेशन प्रॉब्लम है कि पंप का आउटलेट भी अलग अलग एलिवेशंस पे जा रहा है, जैसे स्लोपी लाइन है ना, राइट? हाँ, सो यू हैव टू अकाउंट फॉर दी जो आउटलेट कनेक्शन होगा वो एक किसी पाइप में जाएगा, देन पाइप में पाइप प्राइस एंड अदर स्टफ यू ऑल्सो हैव टू प्रोवाइड. देन मे बी यू कैन डू सम रिग्रेशन बेस्ड ऑन दैट एंड फाइंड आउट द NPSH वैल्यू.
So correct, how to short this?
This you want solution for that, that's what you are saying. Maybe you can mail it to me, I will try to look it into that, but it will take some time for me to answer you, okay?
Yes.
Yeah. So let's get back to our problem again. Result available with error. Okay, so there is some error. Right frac not converted in 20 outside location. Warning in physical property. Computation of the flow rate.
Hello?
Yes?
Your screen is not visible.
My screen is not visible?
Yes.
But I'm sharing it. Okay? Let me reshare it again. Now is it visible? Can you see the Aspen test window now? Yes? Yes or no? I didn't got your...
No.
No? But I'm sharing it. Jamin or Nikhil or Rohan, can you see my screen?
Yes, sir.
You can see. Maybe there is some internet issue in your side, Gaurav?
Yes, I will join.
Okay.
So,
Let me pin this for everyone. So it's already pinned. So let him rejoin. warning bell issue. So there is some error here. Let's just see what exactly this issue is. There has some conversion happened, but then why it is showing an error? Status: material and energy balance failed to converge. Check coal specification or supply better temperature and composition estimate. Let's go and check all the input parameter that we had provided. So number of stages are 8. That is correct. With a partial condenser and a reboiler operating at 22 bar pressure. So feed is entering at this stage number 7. 22 bar pressure is there. Pressure drop is 0. Reboiler data is also correct. Have we added the reaction part? Yeah, reaction is also added. Between stage 2 to 6 reaction is happening. And the rate kinetics, so we have equilibrium based reaction happening in the vapor phase. Yeah, everything is correct. And what's the issue? Let me open a sample example that I'm doing. Yes.
मेरे को एक्सेल प्लस जो है ना उसमें डाउनलोड करने में प्रॉब्लम आ रही है।
क्या इश्यू है आपको उसमें?
तो उसमें ऐसा दिखा रहा है इंस्टॉल के टाइम में विजुअल स्टूडियो का कुछ सेटअप के बारे में आ रहा है, मतलब एरर आ रही है। विंडोज 2010 सेटअप और 2013 सेटअप और XML स्कोर ऐसा कुछ क्वेरी आ रही है, मतलब उसमें
इट कुड बी कि वर्जन स्पेसिफिक हो, क्योंकि दी Aspen प्लस का जो लाइसेंस है दैट इज़ रिलेटिवली न्यू, वर्जन 14 जो सबसे लेटेस्ट वाला चल रहा है वो है। तो आप कौन सा विंडोज़ वर्जन है आपका अभी? कौन सा? सॉरी, विंडोज़ 10। सो वो काफ़ी पुराना है, तो मे बी उसके रिलेटेड कुछ इश्यू होगा। आपने वो इंटरनेट पे सर्च करके देखा क्या इशू को, जो एरर आ रहा है कि क्या एग्जैक्ट इशू है?
हाँ सर, उसमें 2010 का सेटअप डाउनलोड करने का शायद बोल रहे हैं।
ओके, सो मे बी लेक्चर के एंड में एक बार देख लेते हैं आपको आपकी क्वेरी जो है, बिकॉज इट इंस्टॉलेशन इज़ वर्जन स्पेसिफिक, as in it will vary from one PC to other PC also, so it could be any issue. I have to see and then only I can comment what exactly the issue is. Okay. Let me change few conditions here. So instead of what I did was total condense. Run. another, this is also ready. So what I had done here which is different. So maybe the condenser type that I have selected is causing some issue. So here I have selected the total condenser, and for that I was not getting any error. Let me check the reaction part also. Reaction R1, it's an equilibrium reaction. 211. Vapor phase, partial pressure, yeah, everything is same. So maybe because of the condenser type the energy balance is suffering, but then the question has already mentioned that we have both partial condenser and the reboiler, so that should not happen. Let's just see what happens. Red flag not converging 25. Again same error I am getting. What different I have done. We had selected binary parameters using unifact method. Have I done that previously? Yeah, here also unifact method has been used to generate a binary parameter. Method is NRTL only. In the simulation, field 532.78 kilo. This is mole percent, right? Here I have selected mass fraction. Okay, yeah, sorry, this is my mistake. So here I had to change it to the mole fraction. If I will do that, since anyway we have volumetric flow rate provided, and it was instead of mole fraction it was molar flow rate, so it was confusing the Aspen Plus simulator. And then again we can select the partial condenser. So I need a vapor product. Select the partial vapor condenser and let me reset and run the simulation. Now it should work. Okay, while it's loading, let's go to the final question of today's session, which is on case study on the series of distillation column together. So we have been given a hydrocarbon stream H, which is coming at 5 degree centigrade and 2.5 atmosphere, which is pumped via P1, and stream pressure is increased to 10 atmosphere. So from 2.5 to 10 atmosphere feed is pumped, and then it is fed to the series of distillation column. As can be shown here, we have 5 columns. The schematic represents the complete process integration of pump. 5 DSTWU columns are in the series. Feed flow rate is given. Okay, so this is the fluid flow rate condition. For Aspen plus simulation of distillation train, the required information is given in the below table. So for all 5 of this distillation column unit, column pressure and the reboiler pressures are given. Okay, so column pressure you can consider as condenser pressure also, and reboiler pressures are given. Each distillation column has a 20 theoretical stage, including total condenser and reboiler. For light key and heavy key component, 99.9 and 0.1% recovery is expected. In all column, we have to use Peng-Robinson method and then simulate the distillation train and report the composition of all distillation product. So that is our problem statement. In a way it seems a longer, but then it's a pretty straightforward question. It's a number of DSTWU unit in a series. Again I am getting some error. Is any of you is trying parallelly with me? Are you getting the same error? Yes, no? So I'm not sure. The example 3 that I have already tried with is working well. I have changed the data also, but then I don't know why it is still giving an error. Mole fraction, threshold values, flash option we don't have to provide. Stream, condenser, okay. Let me check this, and I will update you maybe in the next lecture why this error has come. Okay, or else I will share this example 3 file. Let me know if you are getting the same error, because I have already done this example with the provided parameters and it was working well. Okay. For the last problem, let's create a new simulation. I don't want to save it. So this kind of a distillation arrangement you will see in the refineries, where you have feed which contains multi-components and they are separated based on their volatility to get a pure component. If you are familiar with the various refining units, you will find that first refining units are this atmospheric distillation unit, vacuum distillation unit, and depending upon how much purity you want, what cut you want, there are series of distillation columns present. Similarly, in the petchem refinery, you will find such train of distillation column units for a separation of a particular component. Okay, so we will add all these components. So first we have ethane, propane, then we have isobutane and N-butane. So let me do a search and quickly find them. So we have isobutane, so C4H10, right? working. I don't know why. Let me try it from here. So we have NC4H10. Then we have isobutane. Then isopentane, N-pentane and N-hexane. Okay. While it's running, you guys have any doubt in this week session or any doubt in general related to how this course is going or the assignments that you are having? Because the problem that I'm trying to solve here are in a way aligning with your assignments so that you should be able to do it. And last week assignment as well as this week's assignment is relatively similar. So if you have any doubt, you can share your concern here also. I guess no. That guy left who had doubt in this Aspen Plus installation. Anyway. So although it's a pretty straightforward method here, so what we will do, we will first create a flow sheet as has been given in the figure 4.1, where the feed will be pumped at pressure of 10 atmosphere and then it will pass to a series of distillation column. Now for each column, as you can see from C1 to C5, they have been given various names. So C1 is a de-ethanizer column, where ethane will be separated. C2 is de-propanizer, where propane will be separated. C3 and C4 are de-butanizer, but that too for separation of isobutane is distillation column C3. For separation of N-butane, we have C4 column, and in the C5 column, isopentane is getting separated. So here in the D1, D2, D3, D4 and D5, we should mainly get ethane, propane, isobutane, N-butane and isopentane. Okay. And the specification is given, like for each component, the light key is what we will get in the top. That should be 99% of the feed composition, and the 0.1% recovery of heavy key. So for heavy key, what we will do now, for the first column itself, the light key is ethane. Then what should be the heavy key? So for heavy key, obviously from C3 to C6, all the options are there, but we will consider its immediate component, which has a slightly lesser volatility than the ethane. So we will consider 0.1% of C3 as an heavy component for the distillate part. Similarly, for in the C2 column, we will consider C3 as a light key component, propane will be our light key component, and immediate heavy key component will be isobutane. And same way we will follow for all the other parts. Okay. Yeah, it's ready. So first, let me go to the property analysis. Component that we have selected. So we have added ethane, propane, isobutane, N-butane, isopentane, N-pentane and N-hexane. All the components are added here. Okay. Method. So the method that has been asked is Penn-Robinson. So if you will see, using the Penn-Robinson property estimation method, we have to simulate this distillation train, run the property analysis, and then for the simulation part, let me first delete this. So you can see, first we will create this flow sheet where feed is coming into pump, where pressure increases and then it is passed to the series of distillation column. Let's see the individual input. So first we will need the stream input. For that we only need the feed condition S1. So S1 feed is coming at 5 degrees centigrade and 2.5 atmosphere, and the mole flow of each component is given in this table. Right? Feed is coming at 5 degrees centigrade, 2.5 atmosphere, and the flow rate, molar flow rate is given. So that has been added here. Once that is done, we will move forward with the pump specification. So for the pump specification, block B1, what we need, so this is working as a pump, and discharge pressure. So we will specify the discharge pressure that has been given as 10 atmosphere. Now here there is no mention of efficiency or pump efficiency or the driver efficiency. So we will leave it as it is. That means Aspen Plus will consider it as 100% pump efficiency and provide the calculation. If you know the specification of pump efficiency for your particular problem, that can be incorporated. After that, from C1 to C, like for all 5 distillation unit, these are the DSTWU unit, as you can see here. All are DSTWU units. So since we want to do a simple calculation of how much separation will happen, so for all component, number of stages has been selected as 20. Pressure condition for the condenser and reboiler is provided in the second column. So here pressure conditions for each column is provided. And then for the light key and heavy key component, so first, right now this is B2. So in B2 we should first get ethane as a product. So ethane will be our light key component. So ethane is selected and recovery of ethane is 0.999% of the feed, and the immediate component with a higher volatility is considered as a heavy key component. So we have selected propane and its ratio is 0.001 of the feed. Similarly for B3, specify number of stages, pressure, temperature condition, light key and heavy key component. Now this part will change and the pressure part will change. Add for all the other blocks, as you can see, till last column where we will get isopentane as a product. Once that is done, you can just run the simulation. And in the stream result, so what are we interested in? We are interested in S8, S9, 10, 11 and 12, all the top part. So in the stream summary, this is the part that we are interested in. Okay, from S8 to S12. Now here you can see, if we will see the mole fractions. So first S8 contains, it should contain the ethane part, right? So the mole fraction of ethane is highest in the S8, right? 0.9985. Similarly, you can see the fraction here, the molar flow rate. If I put the feed flow rate adjacent to it, you can see in the feed we had 35 kilomole per hour flow of ethane, and almost 99% of that came out in the first column itself, and rest was following, it came into the second and third column. Okay, same goes for the propane. So propane should be separated in the second column, that has been done. Then isobutane in the third column, N-butane in the fourth column, isopentane in the fifth column, and you can see almost recovery is around 99% of the feed composition. Now let's say if we want to see this data onto the flow sheet itself, like here, generally along with the flow sheet there are material balance table mentioned below the flow sheet. Okay, so if you want to put that data into the Aspen Plus window, you can select the part that you want to highlight, and in the stream summary option you can see this option, send to flow sheet. Okay, so what this will do, this will add one table of stream summary along with the flow rate. Since there are so many tabs, it's a multiple data, but then you can customize it in and put the only streams which are of your interest. You can delete this object also. So that was the design for distillation column train, where we can find how much separation is happening for this series of distillation column for a given petroleum mixture of ethane to hexane. Okay, so this was the last example for today's class. I will stop here. If you have any doubt in these questions that we have solved, you can ask it out. for the exam how it will be, we will be given with Aspen the software. Selva Kumar, no, for the exam you won't be given the Aspen plus simulation software. So sir has already mentioned it that during the exam, so your assignment contains kind of a two-part question. Like first 5 questions are either theoretical question or this you have been provided snippet of the Aspen plus solution, and based on that there are questions has been asked what is this missing value, what does this signify, okay. And the last 5 questions are kind of related to the simulation where you have to do a simulation and provide the answer. So your exam, the final exam that I'm talking about, will be kind of related to the first 5 questions of your assignment, where it might be directly theoretical based or some snippet of the simulation has been provided and you have been asked to decipher it, okay. You won't be simulating any questions there, since it's not possible to distribute software along all the examination center, okay. Any other questions you guys have? No? Okay. So there were 2 students, Nikhil, who wanted to discuss it, then he has disappeared, and that other guy also, we had a Aspen session. Okay. Anyway, that's fine. So I will stop the recording and you guys can leave now.